Hi there. In this video, we're going to be talking about tangent planes for multivariable functions. And so, wait, you may say, what is this picture about? This looks like a tangent line. So yes, we're going to start with the idea of tangent line just to get some motivation for how this is going to work. But what we need to realize is that when we're dealing with a function of two variables, the graph exists in three-dimensional space. And so when you pick a point and you want to find something tangent, a line isn't good enough. We need a plane. Okay, but let's start with this single variable function and remember how tangent planes worked. Okay, so when I have a single variable function like this, I can choose any number for x naught and look at the corresponding point on the graph, and through that point is a tangent line. There it is. All right, so how can we characterize this tangent line? Well, what we talked about in previous videos was to characterize lines, we need a direction vector. So there's a vector right there. How do we write down the components of this vector? Okay, well, what else do we know about a line? We know it has a slope. The slope is the change in y over the change in x. But the slope, we know from Calc 1, is also equal to the derivative of the function. So therefore, if we just solve this equation, we see that the change in y is equal to the change in x times the derivative of the function. All right, so these are the components of the vector. But we can do something even better, right? We can arrange for these components to be quite nice. We can arrange for the delta x, the change in x, we can make that anything we want, but we can make it equal to 1 if we want to make things work out really nice here. So let's just do that. I'll set delta x equal to 1. So I see that at any point I can form this vector, right, where the delta x part is equal to 1, and the delta y part, the y component of the vector, because delta x is 1, is just f prime of x naught. So now the components of our vector are just 1 comma f prime of x naught. Okay, so important realization that we're going to need when we start talking about tangent planes. All right, so here we are. We're looking at a multivariable function, a function of two variables. Okay, so what we're going to do is we want to find the tangent plane to this graph. And we're going to do that at a point. So we're going to situate this point somewhere, all right, and see if we can find the tangent plane. Now, what do we need to find a plane? We need the normal vector. How do we find a normal vector? Well, if we can find two vectors that are tangent to this surface and take their cross product, that will give us a vector that is normal or perpendicular to the surface. So that's our goal here, find two vectors that are tangent. So what we can do here is we can try to find a vector that's tangent in the x direction. So there we have one right there. Now how do I get that? How do I find that mathematically? Well, this is why we were just talking about the single variable case. We know that if we just take its x component to be 1, then its z component will be the derivative of the function. But it's not just any derivative, it's the derivative in the x direction. And furthermore, the y component will be 0, right? Because this vector is pointing solely in the x direction, has no y component. So the vector's components are 1, 0, and then the x derivative of the function at that point. Okay, then we'll also get another vector in the y direction. All right, so this points 1 in the y direction, 0 in the x, and then the amount that it points in the z direction is the y derivative of the function at the point. So you can see we have these two vectors, and we can do this at any point. No matter where we put this, we can get these two vectors by computing these derivatives and putting them together like that. And then we said that by taking their cross product, we can get a normal vector. So there we are. Now at any point, we have a normal vector. Okay, great. And from that, we know how to write down the equation of a plane. We've talked about this in a previous video. And that is the tangent plane. So if I look here, you can see that that red plane is tangent to the surface. It's just brushing by the surface at that point. It's the best linear approximation to the surface. As flat things go, that's the best you're going to do, right? So if I move this point around, you can see that the tangent plane is going to change. Okay, so let's work through an example. And this is actually the same function that we were just looking at the graph of. All right, so what we're going to do here is we're going to find the tangent plane at the point -1, 2. So let's just take a look at what that would be. I'm just going to situate myself here. So in this, the x-axis is the red line, the y-axis is green. So x is -2. Sorry, -1, and y is 2, so right about there. So we're trying to find this tangent plane right there. I want to find the equation for that red plane. That is what we are after. All right, so what we did is we took the cross product of those two vectors, the vector in the x direction and the vector in the y direction. So the vector in the x direction, let's just call it u. And remember how that was defined. That was 1, 0, and then the x derivative of the function at this point. And then the vector in the y direction, let's call that v, was 0, 1, and then the y derivative at that point. Okay, so let's compute these x and y derivatives. Well, fx, the x derivative of this function, is just going to be, if you work that out, you get x over 4 minus y squared over 8. And if I plug in -1, 2, I get, let's see, it looks like a -3/4. Okay, and then the y derivative, looks like I'm just going to get negative xy over 4. Okay, and if I plug in the point -1, 2 into there, it looks like I get just a half. Okay, so now I know what my vectors u and v are. And from those vectors, I can compute the normal vector n by taking their cross product. How do I take their cross product? Well, we just do this. We take this times this, that's 0, minus this times this. So minus -3/4, that's 3/4. Then I take this times this, that's 1 times a half, minus this times this, that's 0, and I negate that. So it's going to be -1/2. And then finally, for the third component, I take this times this minus this times this. That's 1. That is the normal vector, and that is the vector that we're seeing right here. That's what we just computed. All right. Now we're going to write down the equation of the plane. Okay, well, remember the formula for the equation of the plane is just, you just take n and dot it with x, y, z, and set that equal to n dotted with p, where p is just any point on the surface, right? Any point on the plane, right? Now, what will I use for p? Well, we're doing this at the point -1, 2 in the xy coordinates. So I just need to get the z coordinate now. Okay, so p is just going to be the point, and I'll write it as a vector, -1, 2. I just need that third component, that z component. Well, that's just the height of the graph, right? So that's just the function evaluated at -1, 2. Right? So I just have to evaluate this function at -1, 2. Let's see, what do I get there? 1 minus -4, right? So that's 5/8. All right, so that's 5/8. Right? Just plugging these numbers into the function gives me the height of the graph, and that's the height of the point, right? So that's how I get my plane here. I'll just take these dot products. So I get 3/4 x minus 1/2 y plus z, and then we just take the dot product of these, right? So minus 3/4 minus 1 plus 5/8. Simplifying and clearing denominators, just multiply through by 8 and simplify everything, you will get this. And so that's a really nice way to write down the equation of the plane. That's the plane that we are seeing right here.